Hello, the second video this week is on vector operations. So this is our second day of vectors. And we're going to do many operations with them. Our first example wants us to add vectors together. So we have vector AB equals 2, 3, and vector DF is equal to 1, 4. It first wants me to draw AB and draw DF and show them being added together. So here's how we'll do that. We're first going to draw vector AB, which is 2, 3. So of course our tail starts at the origin. I go right 2, up 1, 2, 3 is my horizontal component. So this is vector AB. Then from there, it wants me to add on vector DF. So DF is right 1. It has a horizontal component of 1 and a vertical component of positive 4. So the head of this vector will be here, which means our resultant vector would look like that. So if we look at the coordinate of our head here, that's right 1, 2, 3. So it has a horizontal component of 3, and up 1, 2, 3, 4, 5, 6, 7. So when we add these two vectors together, we should get 3, 7. All right, let me show you how to do that algebraically now. So in this example, it says that vector AB is equal to -3, 5, and vector DF is equal to 5, -8. And it wants me to write the component form of the resultant, which simply just means your answer. So the word resultant just means it's an answer to addition or subtraction of vectors. And of course, component form is when you have your two arrowheads and you have your horizontal component, your vertical component. So when we go to add these together, you genuinely can add them just like you would. I'm trying to think where you've done this before, and maybe you haven't. But you're going to add your x coordinates together. You saw here that the distance we moved, right 2, and then we wanted to add 1, so we moved right 1 more. So these two go together, and then your vertical components also go together. So you're going to do -3 plus 5, and you're going to do 5 plus -8. So the vertical components go together. -3 plus 5 gives me 2. 5 plus -8 gives me -3. So that's what I get in component form when I add them together. Then, just like the first vector video, we can find the magnitude and direction of this resultant vector. So graphically, it would look like this. Right 2, down 3, and we're finding the magnitude of this purple vector right here, which remember we get by taking the square root of our horizontal distance squared plus our vertical distance squared, just like the Pythagorean theorem. So 2 squared plus -3 squared. When I do that, I get the square root of 13. We have our triangle here, and again, this is just like we did in our first video. So we know our opposite side to our angle, and we know our adjacent side. So we're going to use tangent. Arctangent will give me the angle. So if I do arctan of opposite over adjacent, that would be arctan of -3 over 2. When you put that in your calculator, you should get that this angle here is -56.3 degrees. All right, in the next example, it wants us to add, again, these vectors together. So you may want to pause this and look away from the screen and try this on your own. It's very similar to our first example. You're going to add your horizontal components together first, then add your vertical components together, the -2 plus 6. After you do that, 4 plus -3 is 1, -2 plus 6 is 4. Then here it asks for the magnitude and the direction, so let me do this one more time. We do that by taking the square root of our horizontal component squared plus our vertical component squared. And 1 squared is 1, 4 squared is 16. 1 plus 16 gives me a magnitude of the square root of 17. To get the direction, it may help to see a visual. So this one had a horizontal component of 1 and a vertical component of 4. So this is what our vector looks like. Our tail is here. Our head is up here at 1, 4. So this is 1, this is 4. So when you go to find this angle, you're going to use tangent. And we're going to do arctan since we're finding an angle. Opposite is 4 over adjacent is 1. Put that in your calculator. Arctan of 4 over 1 gives you about 75.96 degrees. So they're saying that this distance from the horizontal line here up to this vector is 75.96 degrees. So that would be our direction. Example 3, opposite vectors. These are when vectors have the same magnitude, but they go in opposite directions. So you can see this here. This purple one is going here down. The green one is the same distance going in the opposite direction. So this is what we refer to as opposite vectors. We denote the word opposite with this minus sign, just like you see a lot when you're talking about the opposite of something, you put a negative in front of it. So it says, what is the opposite of vector AB if vector AB is 4, -2? So it's going to be the complete opposite. It just flip-flops signs. It's almost like distributing a negative. So instead of it being 4, -2, it's going to be -4, +2. So opposite vectors are just opposite in sign. And this leads to subtracting 2 vectors. So instead of thinking about subtracting, you can think of adding the opposite vector. So for instance, if I know AB is 4, -2, and vector DF is -3, 6, and I want to do AB minus DF, you could do it like this, or it may be easier to think about it as doing AB plus the opposite of vector DF, which the opposite would just be +3, -6. Then you can simply add the horizontal components, so 4 + 3, add the vertical components, -2 + -6. You end up getting 7 plus -8. Now I'm going to not do this on this one for the sake of time, but if I wanted to find the magnitude again, I would do the square root of 7 squared plus -8 squared. That would be my magnitude. For my direction, I would do arctan of -8 over 7, and that would give me the degrees of my direction. All right, example 2. Again, you may want to try this one on your own. It's exactly like our last example. This time it wants me to do DF minus AB instead of AB minus DF. So on this one, I'm going to do -3, because that's DF, -3, 6, minus 4, -2. But instead of subtracting, we can think about adding the opposite of vector AB. So the opposite of vector AB would be -4, +2. So if I added these, I'd have -3 plus -4 and get -7. Then I'd have 6 plus 2, which gives me 8. Notice on this one I did DF minus AB. On our last one, I did AB minus DF. And our resultant component form of our resultants were opposite of each other. This one was 7, -8. And this is -7, +8. So on part C, where it says, how does the resultant of vector DF minus vector AB compare to the resultant of vector AB minus vector DF, you would say that they're opposites of each other. They are opposite vectors. All right, next one is on scalar multiplication. So what do you think 3 times vector AB means? Does the magnitude change from vector AB? Yes, it's going to get 3 times bigger because I'm multiplying it by 3. So it's going to get 3 times the size. The direction will not change though. So the scalar multiplication just changes the size, the magnitude. So in this example, it says if vector AB is at -2, 3, write the component form of 3 times vector AB. So you're simply going to distribute that scalar multiplication. That 3, we're using the distributive property to distribute it in. So 3 times -2 gives me -6. 3 times 3 gives me 9. So it's going to get 3 times bigger, 3 times longer. Example 2 says, if vector AB is equal to 5, -3, write the component form of -2 times vector AB. So again, you're just going to multiply this -2 in. -2 times 5 is -10. -2 times -3 is 6. So that's scalar multiplication. This next example is adding, subtracting, and multiplying all together. Vectors can also be written with just one bold lowercase letter. So for instance, in this example, this is the same as saying like a vector A, vector B, and vector C. So we have 3 vectors here. It wants us to find the resultant, so the answer of doing 3 times A plus 7 times B minus 5 times C. So I'm just going to do 3 times A, which is -3, 4, plus 7 times B, plus 7 times B, plus, or I could say minus 5, but remember we could do plus the opposite of this, C. So instead of doing plus, we could have done minus like we have it here, or I could have just done plus and changed everything to positive instead. Think distributive property, multiply everything in. So you're doing 3 times -3, 3 times 4, 7 times 16, 7 times 0, -5 times -7, -5 times -2. And this is what we end up with. Now at this point, you're going to add all of your horizontal components together, which is what's happening here. Then add all your vertical components together, which is what's happening here. And then you get your final result in component form. So 138, 22. So again, just treat these numbers out front as the distributive property and multiply them in. All right, last example. It says from the graph above, write the component form of the vectors A, B, and C. So they're basically asking, where is the head on each of these vectors? So where is the arrow? So on A, it's down here at 0, -1. For B, I would get there by going right 1 and up 2. Because remember, this component form, it tells you the horizontal and vertical distance, but that's also telling you the coordinate to your head. So it's both things. This coordinate here is 1, 2, but it's because my horizontal distance is 1 and my vertical distance is 2. And then C would be -1, 1. Now it says algebraically find the resultant of 2A plus B minus C. So I'm going to do 2 times this A plus B. And instead of doing minus C, I chose to do plus the opposite of C. So I put in a +1 and a -1 here. So I just changed the signs. Add up all the horizontal components. So 0 plus 1 plus 1 makes 2. Add up all the vertical components. -1 plus 2 is 1. 1 minus 1, I feel like that's not right. -1 and I feel like this should be as big as 0 right here. -1 plus 2 is 1. 1 plus -1 is 0. So 2, 0. And I'm not going to worry about you guys graphing it because I don't have you do that. So this concludes our video on vector operation. If you have any questions, let me know.